have here and what
Okay, let's get started. We're just a minute or two late, and we've got a lot of examples to go through today, so you want to get started early. Homeworks are coming back. Overall, you guys did very well on problem 3. Almost everybody got that one right. Problem 4, there were some issues that we'll address somewhat today. And then on problem 1, finding the second law of efficiency, I think threw a lot of people off. So when we're talking about a device like a throttling device or a mixing chamber where it doesn't do any work and there's no heat transfer that's being used for anything of benefit, then the exergy recovered is 0. So our our second law efficiency will be 0. The solution will be posted online. I haven't scanned it yet, but it'll be on this afternoon. So if you have questions about how you did on problems and where you went wrong, then please see the solution for that. And hopefully you started the next homework. Has anybody downloaded it? Okay, download it again because I did change something in problem 4 to make it a little easier. But if you started problems 1 through 3, you'll be fine. So just make sure that if you already downloaded it, just re-download the new copy. Just a slight tweak, and it'll make the problem easier. So you should appreciate that. And again, our exam is 1 week from today. So hopefully you're making your note sheet, you're preparing for that, you're getting ready. Because on Tuesday we're going to do a lot of review problems and work together, trying to solve some equations and work in groups and make sure you understand these topics so that you can be successful. Yes.
Would you care to upload the formula sheet from last semester?
Yes, we send you an email.
Okay.
I don't write stuff down, I don't remember it.
Okay.
Yes.
How many pages do we get that?
You can have 2 pages.
Does that mean like 2 front and back pages?
2 front and back pages, so it's like 4 total pages. So today we're talking about the Brayton cycle, and this is a Stirling engine. I asked to borrow it last lecture, but Dr. Solomon didn't get it to me till today. So this is what I would have used last lecture. And actually on Tuesday he has another cool little engine that uses alcohol and you light it on fire. So he's going to make the lab person come in and do it because of fire. Yes. So we'll have some demos on Tuesday, hopefully, as we do our example problems as well. Okay, so gas turbine engines are primarily used in aircrafts and in ship, and they're used in many cases for propulsion, but also electric power generation. And because these systems are primarily used for propulsion in like an aircraft, their back work ratio is pretty low, meaning that most of the work that's generated by the turbine is used by the compressor. Because we're ultimately not seeking to generate electricity with these things, we want just enough to power the controls or to do whatever we need on board a ship or an aircraft or something like that. But the main goal is propulsion in some of those. So when we're looking at steam turbines versus gas turbines, there are a lot of significant differences. The first one being that a gas turbine is not operating in 2 fluid states. It's always a gas, whereas in a steam turbine you're alternating between a liquid and a vapor. So that's a major difference that makes a gas turbine have a compressor, which then in turn requires a lot more work being put into the system in order to keep the system going. And we'll talk about that a little bit later. But when we compare these gas turbines to diesel engines or steam engines, we notice some positive benefits. One is that they have a higher power to weight ratio. So when used in naval applications in particular, it's very important because you want your boat or your aircraft to be as light as possible. They're more reliable. So again, perfect for naval operations because if you're out at sea and you need to be able to fix this gas turbine, you want something that's not hopefully going to break down, and when it does, it's easier to fix and to operate. So they last longer, they're more convenient, and they can actually offer some high-speed capabilities, whereas a diesel engine, you either get performance or you get hauling power usually, not in both. You don't get both in the same vehicle. With gas turbine engines, you can add some additional components to them that allow you to get high speed when needed, but also still have high power applications. So we'll talk about some of those things today. The Brayton cycle is the primary cycle that we'll study for the gas turbine engine, and it was proposed in 1870 by George Brayton. And originally it was used in oil burning applications, so we don't use oil very often as a fuel anymore, but that's what the original reciprocating engines used primarily was oil. They weren't very efficient, they had atrocious emissions, as you can imagine, so we've improved a lot since then. So today the Brayton cycle is implemented in gas turbines where the expansion and the compression take place using rotating machinery, and the fuel is usually an air-fuel mixture. And they operate on an open cycle where this air comes in, mixes with the fuel, some combustion happens, runs through a turbine, and then there's a hot gas exhaust. But for the simplification of analysis, we often modify that cycle slightly, look at it as a closed-loop cycle rather than an intake and an exhaust, similar to what we did for the auto and the diesel cycles. And if we look at it as a closed system, it simplifies the analysis for us. And we can again apply some of the air standard assumptions that we did for the diesel and the auto cycle. So the actual process consists of 4 stages. There is the intake here, which leads directly into compression. So it's compressed in a compressor, and when it comes out, it's at a higher pressure and goes into this combustion chamber where the air is mixed with fuel. So it's high pressure air mixed with fuel. It's ignited, and the resultant exhaust gases are sent through a turbine where they're expanded and then exhausted to the environment. So this network output is due to these hot exhaust gases being run through a turbine, spinning those blades, and providing some network. However, part of that work has to go back into the compressor to keep the process going. So the network out of our turbine or out of a gas turbine cycle is when we look at steam power plants, which have pumps rather than compressors here. So you remember a steam power plant is operating intermittently between liquid and steam, so it pumps the liquid and then evaporates it. We have to put a lot more of our turbine work back into the system in a gas turbine than we do if we're looking at a steam power plant. So this cycle is approximated instead as a closed system, and this exhaust process we have just put in another heat exchanger for simplification purposes, and we just look at the exhaust process instead of being an actual mass exiting the system. We just are saying we're going to remove all of the heat from this gas-air mixture as it goes through the cycle. And if we apply the air standard assumptions, then in many cases we just use the properties of air as we analyze the Brayton cycle. We don't need to necessarily know or worry about how much fuel is mixed in with the air in the process. Yes?
The spinning rod in the middle,
Yes.
is there any work out from that, or is it just spinning?
It's powering the compressor.
Oh.
Yeah. So it's not physically like that necessarily in a power plant, that the turbine's not directly attached to the compressor, but that's just a way of showing that they're linked, that some of the work out of the turbine is being used to actually to power the compressor.
So they're not physically?
Not always, not usually.
Sometimes.
Sometimes, but usually the turbine is generating electricity, and part of that electricity is used to power the compressor. Because they're not going to be at the same speed and the same rotation, and if your turbine goes down, then your compressor automatically goes down if they're physically linked. Okay, any other questions on that? So it's modeled as from state 1 to 2 isentropic compression, so it's an internally reversible process in the compressor. We're assuming that there's no heat loss in the compressor. Then state 2 to 3 is a constant pressure process, constant pressure heat in. 3 to 4 is an isentropic expansion, and then 4 to 1 is a constant pressure heat rejection. So if we look at the property diagrams for that, you can see that state 1 to 2 is isentropic, so this S value is constant. So is state 3 to 4, we have a constant S. And states 2 to 3 and 4 back to 1 are constant pressure processes. So we have 4 processes, 2 of which are constant pressure, 2 of which are constant entropy. That allows us to analyze this cycle using some of the property relations that we know for isentropic properties of ideal gases. So if we assume constant specific heats, then we can rewrite these property relations as such for the ratio of the temperature between state 2 and 1 is equivalent to the ratio of P2 over P1 to the K minus 1 over K. So this is valid only for isentropic ideal gas with constant specific heat. On your homework, it wasn't a Brayton cycle, it was, I believe, a diesel cycle, maybe auto diesel.
First one.
Auto
First
diesel.
one was diesel, and then the second one was Sterling, and then Harris, and then you had that one that was like that.
On your homework that you just turned in was auto, I think, right? Auto cycle?
Yeah.
So there were some who used this equation to find the thermal efficiency on that last problem, problem 4. That would work if we were assuming constant specific heats. But because we assumed variable specific heats, you instead have to use the relation 1 minus Q sub L over Q sub H. That's always valid. Always valid, 1 minus Q sub L over Q sub H. If it's a totally reversible cycle, then you can use 1 minus T sub L over T sub H, only if it's reversible. And then if it's isentropic ideal gas, constant specific heats, then you can use these thermal efficiency relations for the Brayton, for the auto, for the diesel, all of those values. Okay, so you have to know which assumptions you can make in order to use the equation. So I suggest as you're writing your equation sheet, you write down which assumptions make the equations valid. And then you'll notice on here when we're finding Q in, it's H3 minus H2. So Q is coming in at a constant pressure, but the specific volume is changing. Okay, so this is like a U plus PV term is equal to H. So H3 and H2. The same for H4 and H1. The pressure ratio for the Brayton cycle, this R sub P is the ratio of P2 over P1, which is the same as the ratio of P3 over P4. Okay, so it's the maximum and the minimum pressure in the cycle. So we can, again, use this equation if we're assuming constant specific heats, and if we want to increase the efficiency of the Brayton cycle, there are a couple of things we can do. One is that we can increase this value, this pressure ratio. So that's a positive thing to do, and this is a plot of K equals 1.4 on this diagram here. So the shaded area is showing you the typical pressure ratios for a gas turbine engine. It's usually between 5 and 20. And you can see that the thermal efficiency of the Brayton cycle increases with pressure ratios. So for a pressure ratio of 20, we have a thermal efficiency of about 65%. For a pressure ratio of 5, our thermal efficiency is only about 30%. That's for K equals 1.4. So if we change K, then this line changes as well, which we can do in the Brayton cycle. We can modify K to also change this thermal efficiency. But increasing the pressure ratio sometimes is not a benefit to us, because as we increase the pressure ratio, say we have a pressure ratio of 2 and we increase it to 8.2, this area contained by this curve here is the amount of net work done by our system. So you can see that it increases as we go from 2 to 8.2. Okay, that's a larger volume. However, when we go from 8.2 to 15, it decreases again. Okay, so the area under the curve on a TS diagram, or the area enclosed circumscribed by the cycle on a TS diagram, tells us our net heat transfer, which is equal to our network. So we have to optimize this process. So we have to find the optimal pressure ratio for our particular system so that we can also maximize the work. Because increasing the thermal efficiency is good, meaning your system is more effective at converting heat to energy, but then it sometimes comes at the expense of the total amount of work that you can get out of a system. So again, it needs to be balanced and optimized. The back work ratio is the ratio of the compressor work to the turbine work. So in other words, how much work from our turbine is going back to power the compressor. So in gas turbine plants, it's like more than half of the turbine work is used to drive the compressor. And in steam power plants, that number is significantly lower. So again, there's advantages and disadvantages to both, and we'll talk about both. But for the same power output, a gas power plant requires larger turbines, so it takes up more space than a steam power plant. So other ways to increase the cycle efficiency of any type of gas turbine cycle is to increase the turbine inlet temperature. But of course, you can only increase it to a certain extent before you warp the blades of your turbine. So it's too hot and it's causing metallurgical failure or stress fractures or other problems in your turbine. And having high turbine temperatures also contributes significantly to pollution. You can also look at the turbo machinery themselves, so the compressor and the turbine, and you try to make them as efficient as possible. So you try to improve their performance using aerodynamic models. You can reduce friction. You can use lighter weight materials so the turbine blades spin more freely, different types of bearings. So depending on how much those incremental increases cost your entire system, it may or may not be worth it to increase the efficiency. And then the best way and the most common way, after you've done all of this other stuff and you've tweaked your design, tweaked your materials, removed a lot of the irreversibilities, is that you can add modifications to the basic cycle. So we're going to talk about those today, where you add intercooling or reheating or regeneration, which allow you to get more out of this fluid process. However, it increases, again, the cost of operation and the initial cost of building a power plant to have these additional parameters. Okay, so now every system we know deviates from ideal. We've assumed with the ideal Brayton cycle that the turbine and the compressor are isentropic. However, that's usually not the case. Entropy is created or generated as we operate our steady flow devices. So if we are looking at isentropic efficiencies, this is the same that we found in chapter 7 when we studied entropy, that there's an actual state and an isentropic state. So the isentropic state is if we're assuming our turbine or our compressor is isentropic and our entropy doesn't change as it goes through the steady flow device. Well, in actuality, entropy is going to increase. Whether we're compressing or expanding, our actual state is going to be a higher entropy than our isentropic state. So those isentropic efficiencies are important because we can analyze the ideal state, and if we know the isentropic efficiency, we can find our actual work output as compared to our ideal or our reversible work output. So let's do some examples. We have a lot of examples today that hopefully we can get through them all, but it uses the same base power plant and then we add modifications to it. So we're going to look at this, this Brayton cycle that has gas temperature of 300 K at the compressor inlet, so that would be state 1 is at 300 K, and 1300 K at the turbine inlet, so state 3 is 1300 K. And this additional note on the homework is make sure you read the problem statement and you understand what they're asking you to solve for. So there was one of the problems where it asked to find the temperature and the pressure after the heat addition process. Okay, and most people found it at the state before the heat addition process. So really carefully read the problem statements and make sure you draw on your diagram or indicate somehow what you're actually supposed to be solving for so that you don't do all the work and solve for the wrong variables. Okay. So in this example, we have 4 states, before and after the compressor, before and after the heat exchanger, before and after the turbine, and then this additional heat exchanger here. We know the temperature at state 1, so let's just start there and find our property values from table A17. So if our temperature is 300 Kelvin, then we can look up our enthalpy, and our reduced pressure, because we're going to need that to find the other states. So enthalpy is 300.19 kilojoules per kilogram, and our reduced pressure is 1.386. Okay, we know the process from state 1 to 2 is isentropic, and in this case we can use the air standard assumption, so we're assuming that air is our working fluid. We can, for the isentropic compression of an ideal gas, know that P1 over P2 is equal to PR1 over PR2. So we're told this cycle has a pressure ratio of 8. And if we were to look at the PV diagram for the Brayton cycle, it's something like this. So we have a P high pressure and a low pressure, so P1 is equal to P1, 2, 3, and P2 is equal to P4. No, this is P1, 2, 4. Okay. That's a bad picture, don't look at it. Okay, so P1 over P2 is the ratio of the pressure before and after the compressor, or after and before the compressor, depending on how you want to look at it. So we saw for PR2 is equal to PR1 times the quantity of P2 over P1. And this P2 over P1 is our pressure ratio of 8. And if you ever forget if it's P2 over P1 or P1 over P2, you think about the device. So a compressor is going to increase the pressure, right? So in order for the ratio to be a number greater than 1, then P2 would have to be the larger number. So it's 1.386 multiplied by 8 gives us 11.09. So then we can use that and go back to table A17. So for PR of 11.09, we find that T2 is 540 Kelvin and H2 is 544.35 Kelvin. Now we can do a similar thing for P3 and P4. So P3 over P4 is equal to PR3 over PR4. We solve for PR4 is equal to PR3 times P4 over P3. Now in this case, is P4 going to be higher than P3 or lower in a turbine?
I had a question.
Yes.
So you found T2 and H2 based off of what?
So in table A17, we looked up PR2 and determined on which line that corresponded to a T2 of.
Which was the 11.09?
Yeah, so this value, we looked in the table, we found where that was equal to or in between two lines, and you'll have to interpolate on that one. But so 11.09 is in our table, so we use that to find the temperature in it. We do the same thing for PR4, but in this case, P4 over P3, is it 8 or 1 over 8? So think about a turbine. The pressure higher here or here? Okay, so it's higher at the inlet, right? So the pressure is greater at the inlet than at the outlet because you're expanding this gas and you're removing some of the energy from it to do work. So PR4, whoa. No, not that.
Oh, no.
Now I'm doomed. So PR4 is equal to PR3, which we looked up in the table at state 3, where T3 is equal to 1300 K. PR3 is equal to 330.9 and H3 PR3 is equal to 1395.97 kilojoules per kilogram. So PR4 is equal to PR3 over 8, so this 330.9 over 8. So PR4 ends up being 41.36. So if we go to the tables, that corresponds to a T4 of 770 Kelvin and an H4 of 789.37 kilojoules per kilogram. Okay, so for state 1, we use it to find state 2. We use state 3 to find state 4. And the temperatures are different at those, but the pressure ratios between P3 and P4 are the same, and P1 and P2 are the same. Okay, so temperature varies, but pressure is held constant between those two states. New screen. Okay, so T4 is one of the things we were solving for, the air temperature at the exits of the compressor and the turbine. So we found T4 is 770 K, that's the exit of the turbine, and T2 is 540 K at the exit of the compressor. Okay, now we have all the enthalpy values for our system. So we can say that the back work ratio is equal to the work of the compressor in divided by the work of the turbine out. And that's equal to H2 minus H1 over H3 minus H4. So if we plug in the numbers for that, we looked up H1, 2, 3, and 4 previously, we get that our back work ratio is 0.403, or in other words, 40.3% of the work from the turbine goes back into the compressor to keep our process going. And then our thermal efficiency is equal to work net over Q in. And work net is equal to the work of the turbine out minus the work of the compressor in divided by Q in, and Q in is H3 minus H2. So we have H3 minus H4 minus H2 minus H1 over H3 minus H2 to give us our thermal efficiency, which we find to be 0.426 or 42.6%. Okay, so this is the idealized Brayton cycle. We're assuming that our turbine and our compressor are completely isotropic. So we're going to look at now an actual Brayton cycle. So we'll keep these numbers in mind, this 40.3% and 42.6%, and see how it compares to the actual cycle where we may have some irreversibilities in our turbine and compressors. So now we have, instead of 100% efficiency, we have an 80% efficient compressor and an 85% efficient turbine. So our work actual is going to be equal to our work reversible for the turbine multiplied by this turbine efficiency. And for the compressor, it's going to be the reversible work of the compressor divided by the compressor efficiency. So if we're using a compressor efficiency of 80% and turbine efficiency of 85%, we can figure out these numbers. So this is work actual out, work actual in. So we have 606.6 kilojoules per kilogram multiplied by 0.85 and 244.16 kilojoules per kilogram divided by 0.82. So we find work actual for our turbine is equal to 515.61 kilojoules per kilogram. And work actual for our compressor is equal to 305.2 kilojoules per kilogram. Okay, so our isentropic work was 606, we decreased to 515, and our isentropic compressor work was 244, we increased to 305.2. So seeing this, do you think the back work ratio is going to increase or decrease for the actual cycle?
Decrease.
Increase.
Because it's how much goes back to the compressor from the turbine.
Right, right. So the compressor is requiring more input, and the turbine has less of an input. So the overall result is that the back work ratio is going to
Did
increase.
that have anything to do with it being less efficient?
Everything to do with it being less efficient. Okay, so the actual back work ratio is equal to 305.2 divided by 515.61. So we get 59.2%. Or in other words, almost 60% of the work coming out of our turbine has to go back to power the compressor. So this is the back work ratio. And then our thermal efficiency is equal to the work actual minus, work actual out minus work actual in divided by H3 minus H2 actual. Okay, so how do we find H2 actual? Well, we know our actual compressor work here. So we know if we want to find the actual work of the compressor, it's also equal to H2 actual minus H1. So we can solve for H2 actual is equal to the work of the compressor actual plus H1. So we find H2 actual is 605.39 kilojoules per kilogram. So if we plug in the numbers for that, we have our 606, our 244.16, H3 is on the previous slide, 605.39. H3 doesn't change because the inlets 1 and 3 stay the same, but 2 and 4 are the only two that are changing. The thermal efficiency now is 26.6% compared to 40.3% for the back work ratio before and 42.6. Okay, so our back work ratio has increased and our thermal efficiency have decreased when we look at the actual cycle compared to the ideal cycle. And that is to be expected. Yes?
So is this just a different example, or is this just continued?
It's continued from the previous problem. So it has the same conditions on it. Has the same conditions on it, so the 300K and the 1300K are the same temperatures here and here. But now we're saying instead of having a compressor that works very efficiently and converts as much energy as possible, or consumes as little energy as possible, we now have a non-isentropic compressor. So using the same conditions, now let's assume that our compressor and our turbine are not as efficient as we would like, and let's figure out how much less work we get out of our system and when we look at the back work ratio and how much less efficient the entire system is because of the inefficiencies in the turbine and the compressor. Okay. Okay, so we see the effect of ideal versus an actual cycle on our system. And so let's say we work to increase the efficiency of our turbines as much as possible. We can only do that to a certain extent. They've been designed and redesigned just about as good as they're going to get without completely redefining and redesigning these cycles. So as we looked at the Stirling and the Ericsson cycles from last time, we can sometimes recoup some of the heat from our output or our exhaust and use it to preheat the fluid before it goes into the combustion chamber. So that's what we can do here too with gas turbine cycles, is this high temperature exhaust coming out of the turbine is used to preheat the gas as it leaves the compressor. So we just exchange heat between these two fluids. We're not violating any laws doing that, and we're just preheating this compressor exhaust, you might say, before it goes into the combustion chamber, so that we require less fuel from our combustion chamber in order to increase the temperature before it goes into the turbine. So, although we have turbines and compressors that aren't acting ideally, we can modify our cycle or modify our system to try to improve the total overall efficiency of this gas turbine cycle. Now, this only works if the temperature of the turbine exhaust is greater than the temperature of what's coming out of the compressor. So if the temperature coming out of the compressor is higher already than what comes out of the turbine at the end of the cycle, then it doesn't work for us. And actually, it would serve to decrease efficiency if we tried to do it, because it would make our turbine exhaust hotter and our compressor exhaust cooler. Okay. So it only works, again, if there's a disparity between those temperatures. And the greater the disparity between T4 and T2, the better result you'll have with regeneration in your cycle. So if they're already close to the same value, it's probably not worth the added expense of implementing more machinery in your steam power, or in your gas turbine power plant. However, if there's a great advantage to doing it because there's a high temperature difference between the two, then that's worth looking at and investigating. So this regeneration cycle, we look at the actual regeneration and the max regeneration. So if we're assuming that 100% of the heat that we're removing from our hot exhaust gases is going into the gases as they're coming out of the compressor, we say that our regenerator is 100% effective. So this actual and max, if it just so happens that we have 100%, that means the enthalpy at state 5 and state 4 are going to be the same. So the closer we get to having a 100% effective regenerator, the further this value or this temperature value slides up the scale until the temperature at state 4 is equal to the temperature of this gases coming out of the compressor. Okay, so as T2 and T4 become equal, closer to equal. So the effectiveness can also be rewritten like this if we assume constant specific heats. And again, we can calculate the efficiency of the regenerator, the thermal efficiency, using this equation if also we are assuming constant specific heats. So now let's look at our system again and say, okay, we've got these turbines and this turbine and compressor that are not 100% efficient. They still have these isentropic efficiencies that are less than we'd like. But let's add a regenerator to the system and see if we can recoup some of the difference between the actual state and the ideal state. Now, I want you to note that the addition of a regenerator is not going to have any effect on the back work ratio. It's only going to change the thermal efficiency. Okay. So if our regenerator has an effectiveness of 80%, so our regenerator equals H5 minus H2 over H4 actual, because we're still working with the actual turbine, not the isentropic turbine, is equal to 80%. So we can use this to solve for H5, and H5 is equal to this effectiveness multiplied by H4A minus H2 plus H2 actual. That's the same, H2 actual. So if we plug in the numbers for that, using again the same numbers that we've used all along, then we have an 80% for this value here. Then we get 825.37 kilojoules per kilogram. is our enthalpy at state 5. Okay, so state 5 is in between our compressor or regenerator and our combustion chamber. If this temperature is equal to this temperature, then our regenerator hasn't done anything. But if this temperature is equal to this temperature, then the max amount of heat has been transferred into our fluid. So an effectiveness of 1, it means that T4 is equal to T5. An effectiveness of 0, it means that T5 is equal to T2. Okay, so now that we know our H5 term, we can determine how much heat is required to go now into the fluid in order to have the same H3 value that we had previously. So we're going to reduce the amount of heat that's required because we've preheated our fluid. Q in is equal to H3 minus H5. So we find that is 570.60 kilojoules per kilogram. So now we say our thermal efficiency is equal to the amount of work that we get out of our turbine minus what we have to put into our compressor divided by this new Q value from the combustion chamber. Because our fluid has been preheated, we don't have to add as much Q. So we get this 515.61 minus 305.2 divided by 570.6. We find now our thermal efficiency is 36.9%. So we increased from 26.6%, but it's still not as good as the isentropic case, which was 42.6%. So this is actual with regeneration, and this is isentropic. Okay, S equals constant.
Where are you drawing in the W out and the W in? Like those numbers?
They're the same as they were previously. So our state 3 and 4 haven't changed, and state 1 and 2 haven't changed. All we're doing is saying, okay, we're going to add an intermediate state, state 5. And
So
we,
like
yes.
from the example, like long ago, okay.
So this is the isentropic, or not the, this is the actual compressor, the actual turbine. So this is like state 4 actual, state 2 actual, and then state 1 and 3 is the same in both cases. So what we're saying is, okay, we're going to preheat our fluid coming into the combustion chamber. So then instead of trying to figure out, how much heat is added between state 2 and state 3, we say, well, this is like free heat because it's coming from the exhaust. We don't have to worry about burning fuel to make that heat. We're just going to get the heat now to get it the rest of the way up to the temperature of the turbine. Does that make sense?
Sure.
Okay, oh, I had a whole other slide. Okay, so we can do regeneration, which allows us again to recoup some of the heat from the exhaust to preheat our gases as they come into the turbine, or into the combustion chamber and then into the turbine. So that reduces the amount of fuel we have to burn in order to drive the turbine, which then increases our thermal efficiency. It has no effect on back work ratio because the turbine is still required to power the compressor. The compressor hasn't changed, the turbine hasn't changed. We've only changed the inlet temperature of the turbine using some of the exhaust from the turbine exhaust to preheat it before it goes in. Okay, that's all we're doing. So this net work out is the turbine work minus the compressor work, and we want to maximize turbine work and minimize compressor work. That should be obvious. And if you remember way back in chapter 7, I think it was, we talked about steady flow work being proportional to specific volume. So we did a lot of examples with compressors where we looked at the compressor and said, okay, compressing a liquid is best because our specific volume is smaller. We like to have pumps in a steam power plant for that very reason. But we can't do that in a gas turbine plant, because liquefying gases requires very cool temperatures, and that's makes it almost impossible to run it. So this idea of decreasing the specific volume in the compressor, we looked at several different options of doing that. One, we could cool the gas as it's passing through the compressor. We could cool it so much that it becomes an isothermal process. That would be the ideal case. But in reality, it's very difficult to cool as you're compressing. So we compress to an intermediate point, cool the gas back down, and compress it again. Okay, that's called intercooling. And we did a lot of examples of that last semester, so you can look back on those slides if you need a refresher on that. And it's because we want to minimize the amount of work that the compressor has to do. And if we decrease the specific volume in between two stages of a compression process, the total overall work is less. Now, we want to maximize the work output of the turbine. So another way of doing that, instead of seeking to minimize the specific volume, we want to increase it. So instead of cooling in between stages of a turbine, we would reheat. Because as the gas passes through the turbine, it necessarily cools down. We can instead do two stages of a turbine, heat the gas up in between, and pass it through a second turbine. Okay, so it's analogous to what we did with compressors. We're going to cool the gas, and it's not convenient to cool it as it's being compressed. We do it in intermediate phases. The same thing applies for a turbine. It's not really convenient to heat the gas as it's being expanded in the turbine. We expand to a certain state, heat it back up, and then expand it again. So this is multi-stage compression and multi-stage expansion with intercooling or reheating depending on what your desire is. And so we can implement this, and again, it's one of those optimization problems where we try to determine how much additional work and net benefit we get by implementing these strategies versus how much it's going to cost to produce or to build in the outset, and then considering maintenance costs along the way as well. So if we were to look at that, this is the modified Brayton cycle with intercooling, reheating, and regeneration. So we have two compressors, and again, in between the compression processes, we cool down the fluid so that our specific volume is lower, which means it requires less work to compress it to the same pressure. Similarly, we have two turbines, and in between the turbines, we reheat the gases so that we increase the specific volume so that we get more work out of the fluid as it's passing through. We can also implement regeneration as we did before, but it only happens at one point, prior to the combustion chamber. Okay? The reheater is different than the combustion chamber. The combustion chamber has to take it up a larger temperature, increase the temperature a greater amount. Okay, so as we come out of this turbine, we can put those hot gases through this regenerator, which takes the exit of the compressor and heats it up. Okay, so whether we have one compressor and one turbine, or two compressors and two turbines, it's always the outlet of the final turbine and the outlet of the final compressor that we use in the regeneration process. It's not often that you have multiple regenerators. Usually it's just done one time. And we derived the expression in prior semesters that the work will be minimized when our ratio of pressures across the compressors are the same. So when P2 over P1 is equal to P4 over P3. So this intermediate pressure that we compress to is important. And then the same holds true that the work will be maximized when the ratios across those two turbines are the same. So we can look at a property diagram, and then you can see here how this varies as from the original diagram, because we have these intermediate steps here. From step 1 to 2, if we have an isentropic compression process, then we then we cool our gas back down and compress it again. So the temperature increases, we cool it down, then we increase it again. Then we go from state 4 to state 6, passing through the regenerator along the way. So this heating occurs because of the regenerator, rather than requiring the combustion chamber to take it all the way from state 4 up to state 6. So then when we get to state 6, we're right here at the entrance of our turbine. We expand the gas, the temperature decreases as we're expanding, so we want to heat it back up, and then it decreases again as we expand to state 9. And then again, we go from state 9 to state 1. Some of the heat is removed from this turbine gas, so it cools down back to the temperature of the inlet to the compressor. And again, even though this is an open system, we model it as a closed system with air as the working fluid. So we use that air standard assumption again. Okay, any questions on these processes? It starts to look very complicated, but the analysis is not that bad. Okay, it's really not that bad. Yes?
So let's say on like state 1 to state 2,
Yes.
if you screw up the properties from the very beginning, then I'm assuming you're just going to screw it all up from the rest.
Well, not totally, because usually you're given like a temperature here and a temperature here. So if you screw up somewhere in here, you screw up in between the compressor and the regenerator, you can start over again at the turbine at state 6. So you only maybe mess up this half of the problem.
Unless you're worried.
You're worried about it, I can tell, Blake. It's okay.
Yeah.
Because you know how to analyze compressors, right?
Sort of.
You know how to analyze steady flow devices. You just have 2 in a row now. And because we're making some very specific assumptions like the pressure ratios are the same, you really only have to analyze one of them and then you double it. So we'll look at that as we do the example. Any other questions on this or comments? It's going to be a big, ugly problem on the exam, so just be prepared. Just kidding, I haven't written it yet. But that gives me a good idea. Okay, so we can do this almost indefinitely. We can keep adding compressors and turbines and just keep drawing this process out as big or as wide or as far as we want.
So do you get
Yes.
more energy, so like say you have a power plant like that, in theory.
Yes.
So the more you add, is it necessarily the more power you're going to get?
That's the idea. That's why you're adding these additional components. So the balance comes in with how much it costs to add these additional components versus how much extra power you're getting out.
So like if you add like a turbine 3,
Yeah.
does that mean you have to add a compressor 3?
Not necessarily, because they're 2 separate processes. So, I mean, if you like feng shui and you need things balanced, then you would add another one. But you don't you could have 5 compressors in 1 turbine. Okay, so this part of your process will be optimized, whereas this will be less effective than it could be. And again, maybe it's cheap to put in compressors and expensive to put in turbines, so you try to get your gains here. You try to minimize compressor work, because here you're seeking to decrease the amount of work that's required, and here you're seeking to increase the amount of work that goes out. And either one of those that you do is going to overall increase your net worth. And because the compressors really do require a lot of back work from the turbine, even if you just focused on decreasing the compressor work, you would have positive gains in your system. Whereas in a steam power plant, trying to make the pump more efficient is probably not going to be a good value for your time spent, because there's big gains to be had in increasing compressor efficiencies.
So for this, like where the regenerator is that like a heat exchanger at all? Or
Yeah, that's exactly what it is.
So the temperature of 9 and 10 has to be higher than 4 and 5?
Yes.
Okay.
Well, the temperature of 5 could be exactly equal to 9. So if you've transferred all of your heat from your regenerator into your, you know what I mean? Like if all the energy from that exhaust transferred into your compressor, the fluid coming out of the compressor, then ideally 5 would be 9. So you would have 100% effectiveness in your regenerator. But yes, this temperature 4 has to be below temperature 9 or it wouldn't work. And again, the greater disparity between those 2 temperatures, the more worthwhile it is to put in a regenerator. If they're just a couple of degrees different, it's not going to be worthwhile. Okay, any other questions on this? Okay, so we can keep adding regeneration processes if we wanted, and these little sawtooths can get smaller and smaller and smaller, and you can see that it looks like the Ericsson cycle. Okay, so this is the Brayton cycle with 1, 2, 3, 4, 5, 6, 7, 8, 9 interheating and cooling processes. And as we continue to add those, then it can be more closely approximated by the Brayton or the Ericsson cycle, which was a reversible idealized cycle that we can't really implement in practice unless we get really complicated with our Brayton cycle. Okay. So it's never going to be a flat line, but we get the same overall trend. All right, let's do an example, and you'll see it's not so bad. It's 2 pages long though. Just because there's a lot of stuff. Okay, so from before, we had state 1, and because we don't want it to be overly complicated, we're looking at the idealized versions of the compressors and the turbines. So we're not worried about isentropic efficiencies. So this is like if we went back to the original example 1 where we had the ideal cycle and then we added stuff to that one. Okay, so state 1 is the same as state 3. So ideally with a compressor, if we're dividing it into 2 stages, we're increasing the temperature as we compress it, and then we cool it back down to the same temperature of state 1. So state 1 and state 3 are the same. T1 is equal to T3 is equal to 300 K. H is equal to 300.19 kilojoules per kilogram. And P sub R is equal to 1.386. Now state 6 and state 8 are also the same. So state 6 is here. This is 1300 K. So T equals 1300 K. H is equal to 1395.97 kilojoules per kilogram. And P sub R is equal to 330.9. Okay, so we've already looked at 4 states, and we just had to look up 2 of them, right? So not so bad. So now state 2, which is also the same as state 4. Okay, in order to find those, we have to use the pressure ratio PR1 over PR2 is equal to P1 over P2. Okay, so here's where you have to really remember and understand pressure ratios and what it means for a 2-stage compressor. Because the overall pressure ratio is 8, which means that the pressure across each stage is going to be the square root of 8. And that's to have the maximum possible scenario. So if P1 over P2 is equal to P3 over P4, then it equals the square root of the pressure ratio 8, P1 over P4. And that's from chapter 7. Okay, so then we say PR2 is equal to P2 over P1, PR1 equals the square root of 8 times 1.386. So that's our PR1 there. So that gives us T2 is equal to 403.3 Kelvin, and H2 is 404.31 kilojoules per kilogram. Okay, and fortunately for us, state 2 is the same as state 4, so that helps us out a lot. Which is 404.31 kilojoules per kilogram. Okay, and that's because our PR2, when we solve for it, is 3.92. All right, so now we have state 1, state 2, state 3, state 4. We need state 5, and we need state 7, and we need state 9. Okay, state 5 will come in a minute, but let's look at state 7 and 9. So we don't know the temperature, enthalpy, or reduced pressure yet, but we can do the same thing that we did for these ones. Okay, so PR7 over PR8 is equal to, sorry, that's a 6. PR7 over PR6 is equal to P7 over P6. And again, PR7 is equal to P7 over P6, PR6. We know PR6 from here is the same as state 8, and we know that P7 over P6 is going to be 1 over the square root of 8 times 330.9. So we get our PR7 is equal to 117.0. And that corresponds to a temperature 7 of 1006.4 Kelvin, and H7 of 1053.33 kilojoules per kilogram, and the PR117. So look at that. We've already found states 1 through 9, excluding 5, and we didn't even do that much work. So chill out, Blake. It's not that bad. Okay, so now we're looking at the work of the compressor in is equal to H2 minus H1 plus H4 minus H3. So it's H2 minus H1 plus H4 minus H3. Those two compressors together give us all of our compressor work. We have all of those values, so the compressor work in is equal to 208.24 kilojoules per kilograms. And this is case A, so we're assuming that there's no regenerator right now. The work of the turbine out is equal to H6 minus H7 plus H9 minus H8. Okay, so H6 minus 7, H9 minus 8, no, 8 minus 9, 6 and 8 minus 9. Which gives us 685.28 kilojoules per kilogram. So we can find our work net is equal to the work of the turbines minus the work of the compressors, which is equal to 477.04 kilojoules per kilogram. Okay, so we have our work net. We need to find our Q in. Well, we don't have to find that yet. So our back work ratio in part A is equal to the work of the compressors divided by the work of the turbines, which gives us 208.24 over 685.28 is 30.4%. So when we compare it to example 1, our back work ratio was 40.3%. So we were able to decrease our back work ratio, which is a good thing. Okay, it means only now 30% of our work from our turbine has to power the compressor. And our thermal efficiency in part A without regeneration is work net over Q in. And Q in I solved earlier. Let's solve it real quick. Q in is equal to Q of combustion plus Q of reheat. Okay, so if we look at that picture, we have a Q in here and a Q in here. So combustion and reheat. So the combustion process happens between H6 and 4, and the reheat happens between 7 and 8. So we have H6 minus H4 because we're ignoring, for now, a regenerator, H8 minus H7. So Qn is equal to 1334.3 kilojoules per kilogram. So let's put that back in our thermal efficiency equation. Work net over Qn, 477.04 divided by Qn, which was our 1334.30 kilojoules per kilogram. So we get a thermal efficiency of 35.8%. And if we compare that to example 1, our thermal efficiency there was 42.6%. So why do you think our thermal efficiency decreased? We've got a greater work production happening, but our thermal efficiency is decreased. Not time yet. Any thoughts?
Because like there's more.
Yeah. Well, there's more steady flow engineering devices involved. So every time you add a compressor, add a turbine, add anything, heat exchanger into your system, you're decreasing the efficiency of it. So again, balancing efficiency with network out. So our efficiency decreased, but our back work also decreased, which is a positive thing. Yes.
Why was the pressure ratio the square root of 8?
So if we go back to chapter 7, it's we did an optimization problem where if we look at the compression in 2 stages and we have P1 over Px and Px over P2, and we solve for P sub x, it's the square root of P1 over P2, or P2 over P1, P2 over P1. So that's where that comes from. So if you look back at that, you can see that. Okay, so then let's look at it real quick with a regenerator. Here we're going to have an effectiveness equal to H5 minus H4 over H9 minus H4 is equal to 100%, which means that H5 is equal to H9. So Qn now is equal to H6 minus H5, which is also H9, plus H8 minus H7. We put in numbers for that, we get a Qn of 685.28 kilojoules per kilogram. So we've reduced the amount of heat we have to put into the combustion chamber. So now we calculate our thermal efficiency as work out over Qn. Our work out doesn't change because of our regenerator. What changes is Qn. And we find that our thermal efficiency has increased to 69.6%. So we're complicating things. We have to make sure that the gains are worth it. Okay. We can also do the second law analysis of gas power cycles, which we're not going to do today. We're going to do some examples of that on Tuesday. It won't be on the exam, just so you know. There may be some other questions involving exergy destruction, but it won't be with Brayton cycle. And then jet propulsion, just a few comments on this, because we're using gas turbines oftentimes in aircraft. And as I mentioned before, the ultimate goal isn't to have a network output, it's to have thrust. So the output is generally primarily for thrust, and there's just a little bit that we use and goes entirely back into the system. There's no energy generation, so our net work out is zero. And we use it to fly airplanes or jets. And so they're propelled because we're accelerating fluid in the opposite direction of aircraft motion. So the turbine, rather than accelerating blades to do work, they're accelerating blades to push more air out. And we can make modifications. You can read a little bit more about this in your textbook. This is just FYI kind of stuff. We're not going to be tested on any of this. But it's interesting to look at the changes that you can make to modify these gas turbine engines and make them linear and then use them to propel something forward rather than to generate energy. So look at that on your own time, and I'll see you on Tuesday.
Can you go back to the end of the last example?